Hello everyone, welcome back. So in this lesson, what we're going to do is to go over some coding for the hypothesis testing. So in R, there are many different packages and also many different ways to do hypothesis testing. We are just showing you the basic R functions here in this lecture, but if you find anything that is useful for you to understand and solve the problem, feel free to use it, right? So you're not limited to just use the base R functions in this class. Well, let's take a look at today's example here. So what we're trying to do today is basically getting an idea about how we can use the probability functions and trying to make conclusions about the hypothesis testing process. So the first thing we're going to do in this example today is to generate some random normal distributed data. So I'm going to generate 1,000 data points that has a mean values 1,250 with a population standard deviations of 158. So let's generate that. So I would like to also select a small group of samples from this 1,000 points. So in this case, I'm selecting only 10% of the total sample here, which is 100 observations from the 1,000 population data. And I call this sample.cells. So I'm going to randomly select the sample here. Now, what you're going to do is basically test how likely this set of sample might be giving you a high chance to be included in the population means. So what it means is, well, I want to know, are we going to randomly bump into this mean value that we selected from the population data, right? So this 100 data point is going to generate mean values, but are we just bump into this extreme large mean value or extremely low mean value, or are we usually going to get some number around this range, right? So let's take a look at our hypothesis today. So the hypothesis we are trying to test out today is, well, the sample mean will have a same value as the population means. The alternative hypothesis basically say the sample means is not equals to the population means by chance. And we want to test with some confidence in this hypothesis testing. And the confidence level here is 0.05. So what the confidence level here, or alpha, means is we accept 5% of the time that we are wrong in our assumptions for the null hypothesis. So if we are confidently say that, hey, you know what, we bump into this situation, I think, well, we are correct on this, but I'm still bearing 5% of the risk. Am I willing to take it? If I'm willing to take it, then, well, the null hypothesis will be correct. However, if it's too risky, let's say, well, somewhere go over 10%. Let's say, well, our results, our p-value return from the hypothesis testing tell us there is 10% of a chance that we can get wrong, then obviously we cannot trust the null hypothesis anymore. So we have to go to the alternative. That means, well, the sample means cannot be equals to the population means because it's just too risky to believe it. Well, this is a totally simulated situation here, and you know the result is going to be follow the null hypothesis for sure. However, I want to show you the steps to do it so that you can actually understand how it's going to be done. So first of all, I would like to actually calculate the means for the cells, which is the total populations from the 1,000 samples. And I want to calculate also the cells mean for the samples and the cells standard deviation from the samples, and as well as the n, which is the total observations or samples in our sample sets. Not the population, but the samples. So let me just run this for codes right here. Okay, so I store the values into R. So what I'm going to do is basically applied what we learned last sections. Remember, to see the probability in a distribution, we have to first figure out the locations of the distributions. And this time, we assume that we do not know the population standard deviations, even though we specify in our simulation data. But we just assume that I don't know, right? So the standard deviation is unknown. I'm going to focus on just using the t-statistic in this case. So we're going to use the sample sales mean minus the population sales mean, and divided by the sample sales SD, the standard deviations, divided by the square root of number of observations, n. So I calculate this, and I'll get the t-value here, which I can print up. So the locations here is negative 0.3492 or 3491. If we look at the t-distributions diagram again, so you're basically looking at a location somewhere closer to actually closer to 0 here, between -1 and 0, closer to 0, right? So it's negative 0.349. Right, so well, I want to know, right, what's the probability that we can actually get a sample means equals to, right, to this range. So I would like to basically calculate what we call a p-values of the problems. So the p-values basically represents the probability of the two tails at the confidence level we are willing to accept. So in this case, what it means is I want to compare it to the 5% level, right, of confidence. Each side will be 2.5% on the left or right. And I'm going to use the t locations right here that I just calculated and put it into the graph and trying to compare it to the alpha level, how risky we are willing to take, right, willing to take in this hypothesis testing. So to do that, I'm going to basically calculate the one of the tail, right, given the t locations here, with the degree of freedoms n minus 1s. And I'm going to use 1 minus that value so that I can get tailed probability. Once I getting the tail probability, I can actually multiply that by 2, then I will get the total sense of how great the p-value is on two sides of the distributions, given the locations of t, right? So let's run this and try to see what the return result is. All right, so I'm getting a result of, so I think something wrong right here. I guess it's on the negative side, so we don't have to do -1, so my bad. So let me just run this one more time. Okay, so that makes more sense. So now I can actually see the two left side and right side tail combined will have a probability or p-value equals to 0.7276, which is 72.76%. It's huge, right? So we are bearing a very high risk that to say that the null hypothesis is not correct. Well, how much risk we are willing to take? If from the very beginning we specify, we are only willing to take a risk of 0.05, which is 5% of a chance to get wrong. However, the t-values or this whole calculation tell me, well, if you want to say that the sample mean is not equals to the population means, I'm bearing 72.76% of a chance that I will be wrong, right? So I cannot actually confidently say that conclusions. So that's why at a 5% significant level, because we compare it to 5%, it's just too large. The p-value is too large. We failed to reject the null hypothesis. So the sample mean is not statistically significantly different to the population means. So they're basically the same thing in general, because, well, it's very, very possible that we can just randomly draw 100 samples to bump into this mean values. Well, another solution to this hypothesis testing is to use what we call the t-test functions. So again, the t-test function basically give you the capability to do all these calculations by hand in just one line of code. All you need to put into this t-test function is to specify the samples, right? So our sample, it's basically the 100 random sample we draw from the sales data. You specified the 100 point right here on the first locations, and you want to define the mean of this t distributions. And this mean, it's basically using the parameter of mu. So the population mean, or mu, is the sales mean that we calculate earlier. So again, this line right here. So again, to sum up, in the t-test format, all you need to do is basically put in the sample data sets into the first locations and defining the population mean, which is the mu, and in this parameter. So let's run this and see what returns. So in this t-test functions, it returns several important things that you should know. Number one, we know that the t location is negative 3.4926, which is exactly what we calculated earlier. And the degree of freedom, it's 99 because we have 100 observation minus 1. The p-value is 0.7276 for two-tailed tests. And here is what we calculate earlier. So as you can see, well, this t-test actually has a output that is very nicely presenting all the statistics we just calculated in just one line of code. However, again, you have to understand when you use the procedure for calculating all this value and when you can use a t-test functions. The t-test function only available if you are having the data sets to input to the functions, right? In this case, I'm not inputting any mean values or standard deviations. I'm using the whole data sets from the samples. And I'm defining the only one thing is the population mean values in this t-test functions. If you are only given, let's say, the mean of the sample, the mean of the population, the standard deviations of the sample, and the number of observation, but you don't actually have the data sets, you cannot use the t-test functions to calculate the p-values to test your hypothesis. Okay. Well, another important thing to learn in this class, I think, is try to learn how to plot or to make some very nice visualizations for your hypothesis testing. So specifically, I would like to use a library called MASS in this example. So MASS it's a library that contains many different data sets that you can use. And today we are going to use a specific data set called survey. And to basically add a very nice hypothesis testing graph in your study, you can actually import this package called GG Inference. So I'm going to import that too. All right, so let's see what we can do. First of all, I would like to load the data from the MASS data sets. I know there is a data set called survey, and I just want the height from this survey. And I'm using the na.omit functions, basically means we'll drop anything that is not available, or basically it's empty, right, in the data sets. So I'm going to load this, and I'm going to save this height into a variable called h. And I'm going to basically calculate the means for this survey data and save it as PM. Population mean, basically, right? So PM, short for population mean. Now, what happened is I want to randomly draw some 30 samples from this data, my survey data, H. So sample functions, and I'm going to draw it from H. I only want to select 30 of them randomly, and I'm going to save it as h.sample. So I save that, and I'm also calculating the mean value for the sample. So I call this SM, so mean of the h.sample. So now I have almost everything that I need, right, for our study. Of course, you can print the sample means and the population means, right? So PM is going to be 172, and the sample that we draw here is 170, right? So we want to actually perform a two-tailed test in the t-distributions on this random samples. So what I'm going to do is to use the t-test functions, because I have the sample on hand, right? I have the 30 observations here. What I need to do is to put in the observations, the 30 observations, and then define the population mean, which is mu, and I use PM to save. And I'm going to store this into a result right here. So let's see what the result is. So the result tells us the probability, right, the p-value that we are going to say the null hypothesis is wrong will involve 44.345% of a chance that we are wrong. So if we want to prove the sample means is different than the population means, we have to have 44.35% of a chance that we get this statement wrong, right? Obviously we cannot confidently reject the null hypothesis in this case. However, that's not what we are trying to demonstrate here, right? So we want to actually see how we can plot this result. So what we're going to do is to use the GGT test results functions and put in the results that you just did with the t-test, right? So let's see what it returned. So very nice. So as you can see, this GGT test, it's a plotting function. It automatically plots the t-distribution for you and also pointing out the locations in your test. In this case, negative 0.7768 is the locations from your t-statistics. And the probability of the two tails with 5% confident intervals, it's located at negative 2.045 and 2.045. And this samples that we are selecting, obviously it's within this middle sections right here. So we cannot reject the null hypothesis. It has a significant difference to the population means. So we can definitely randomly select some number from the population and bump into this mean values. So again, you can also do a one-tailed test, not always a two-tailed test, right? So for example, I want to actually do a one-tailed test for a t-test, and we put in the samples that we draw from the populations, and we are going to define the mean, the mu, in this case, mu is equal to PM, right? And we are basically given the alternative in this test. So the alternative is we want to do something greater. So that means we want to actually have a one-tailed test on the right-hand side. So we're testing on the right-tailed test here in this case. Greater, right? I mean on the right-hand side. And confidence levels, 95%. So that means we are satisfied with 5% of a chance to get wrong, right? 95% confidence to reject the null hypothesis. So we're going to save this result. And here, you can get the p-value here, which is 0.7782. And the t locations is going to be negative 0.7768, which is everything the same. But the null hypothesis, it's basically different because the alternative says the mean is greater than this value, 172, which is the population means. So again, the chances that we can reject the null hypothesis is just so low, right? We cannot confidently reject the null hypothesis, because if we do, there are 70.782% of a chance that we are wrong in that statement. So we cannot reject the null hypothesis So we have to trust it, we have to believe it. And that means, well, the alternative hypothesis cannot be true, right? This is not true. Again, well, using the TT test, right, or GGT test plot functions, this time we can see we have a one-tailed test on the right-hand side, and the locations of this one-tailed test is 1.6899. Well, the difference between the two-tailed test and the one-tailed test, it's literally just the locations of the t-scores. Because when we putting 5% of the weight on two sides, well, each side will only contain 2.5%, which will make the location much further away from the center. However, if we only putting 5% in one tail, in this case, well, the probability, right, the density on the right tail will be larger. That means the locations that described that probability on the right tail will be closer to the center point of the distributions. And in this case, it demonstrates the location will be 1.699 comparing to a 5% two-tail, each locations will be 2.045. So those are the graphical tools that you can use, right, very conveniently for your analysis, right, especially for hypothesis testing. But the general idea is, well, to apply the hypothesis testing process, state your null hypothesis, state your alternative hypothesis, calculate the t-scores, t-statistics, and then compare it to your criteria for rejections, which is the alpha. How much risk are you willing to take to reject the null hypothesis? And at last, to make a conclusions, right, whether you reject the null hypothesis or not. So again, please practice this tool. Many people actually will find this t-test function much more useful than the regular p-value approach. But either way, I would say, well, it's not going to be that difficult to do, even for the p-value approach, especially when your assignment sometimes may not be given the data sets to test it. So again, today we're covering a lot of materials. So if you have any questions, feel free to contact me, and I'm more than happy to answer your questions. I will see you guys in the next sections. Goodbye.